All right, everyone, we are going to be doing our uh, simple harmonic motion of our cart and two spring system lab. So, just like we talked about at the end of our lecture, we're going to be looking at a system, basically a vibration system. So, what does that mean? We're going to be looking at a system where we're going to attach a cart here that has some mass, M1, to a spring. We'll call that with a spring constant K1, and then another spring with a constant K2 that's attached to another wall. So our cart will have wheels and it will roll back and forth. So if we define our coordinate system, x, y, positive moment as we always do, if we were to take this cart and displace it some amount delta x in this direction, so basically if we were to accelerate this cart, so some mass acceleration in this direction, what would happen to our springs? So let's go ahead and let's take our body. Let's free it from the surrounding. So FBD. Our kinetic body diagram, there's no rotation. So we have our cart and it's going here. And there's going to be some, at some, G, some mass and some acceleration here. So our free body diagram, well, when we extend the cart like so, there's going to be a force of our spring. So some force is going to be going in this direction. That force is going to be minus K1x, or some delta x effectively. On the other side, when this spring is compressed, it's going to be also pushing. It's going to basically, again, if our cart moves here, it is going to be compressed, and actually it's going to also push in this direction. So there's also going to be a force minus K2. Actually, we can draw it like this. Minus K2x. So times x here, effectively. So we can write our free body diagram because, again, we're compressing the string here. We're elongated. It's going to want to pull the cart back. On this side, it's going to want to push it forward. So if we do now, our sum of the forces in the y direction must be equal to mass times, or in the x direction, excuse me, mass times acceleration in the x, which is going to be equal to minus K1x minus K2x. We're going to replace this with our other notation. So mass times double dot of x, because we'll do that notation, minus K1. Actually, we'll do this. Here, I'm going to erase that there. We'll do minus K1 plus K2. We'll leave the whole thing in there. Minus K1, K2, K1, K2, x. So, and we could actually bring that over, and we can actually see our natural frequency now. Actually, we can say that x double dot, x double dot plus K1 plus K2 over the mass times x equals 0. And we know that in this form, which we've worked with before, our natural frequency, omega, and remember, omega equals 2 pi f, and this will have the form of basically a sinusoidal basically solution. So our x of t will look something like a times sine of omega nt plus b cosine of omega n times t, where omega n is equal to square root of K1 plus K2, over M1, 1, mass 1. And so our x as a function of t will look sinusoidal. And it will have some period here, and that period, the time between this peak and this peak, will be our period t, which can be in seconds. Our cyclical frequency, is going to be 1 over t, and that's going to be our value in hertz. And we're going to convert that omega equals 2 pi f, and that's going to be our frequency in rads per second. So we can actually also prove that as well. So I'm going to delete everything in here. I'm going to quit our kernel locally, and then I'm going to say desolve, because our function is x of t plus K1 plus K2. I'm going to divide this by M1. Divide by M1 times x of t. Set this equal to 0. Solve for x of t, variable t. And we'll see our expression will look something similar to this. It's going to solve. It's just taking a little while. Mathematica's just waking up. And actually we can see here, again, this can just be broken down into basically cosines and sines. But we can actually remove those out of there. Let's go from here. Let's do here. And these are just, again, they'll be sines and cosines. There's just Euler form here that you can kind of plug those in. But that is it. So now we can go ahead and start to solve our problem here. Fantastic. All right. We will see you all in the next, or actually not in the next video. So what we're going to do now is we're going to actually look at how we're going to set up our lab. We're going to gather our data, and then we are going to compare. We're going to measure the actual experimentally derived circular frequency, omega, instead of the cyclical frequency. So we're going to measure the displacement versus time of our cart with our known mass, with our known K and K2, and we're going to go ahead and compare our experimental frequency with a theoretical one to see how those two compare. So let's get to running our lab. Hi everyone, we are back and we are going to go ahead and start our vibrations lab. So our second lab in this series. So last time we dealt with statics. Now we're going to be dealing with vibrations. So we're going to use our Vernier, basically cart system. You see here we have our two hooks basically here. This is going to measure our actual displacement, and it will actually also look at and well, it'll calculate acceleration, velocity. So it's a really, really, really nice system. You can see the positive x direction defined here. It's a wireless, basically connection, so we won't have to plug in directly like we previously had to do with our force sensors. So now we can go ahead and we are going to look at the natural frequency and calculate the natural frequency of a mass and a two-spring system like we've already basically shown schematically, or, you know, in a diagram in the previous part of this video. So these red springs are 10 Newton meters. The mass of our cart is approximately 250 grams, but it may be a really good idea to basically look at that and basically measure that ahead of time. So first thing we have to do, we need to turn this on, and actually you can see it's on by that red dot. So we're gonna go to our system here. We're going to find our wireless device setup. We're going to click on Go Direct. So let's go to Sensors again, Wireless, Go Direct. And now it's going to look for our Bluetooth. We're going to want to connect here. Once it's green, we can see our cart. Click on it. You want to double check, obviously, with this number here. Let's see if I can focus in on it. Make sure that those numbers match. Let's see if I can kind of... Yeah, here we go. That number, make sure it matches with basically that number here. Sorry for the quick zoom in. So let's go ahead and press OK. We're going to connect. And let's go ahead and zero out our cart. And we can see here, like at the center of this cart, it's probably around like 61, 62 and a half. So if I go to, for example, to 22, we can see it's about 0.1 meter in the negative direction. If I go to 48, actually, or 52, excuse me, it's about 0.1 in the positive direction. And these are centimeters, so again, that should kind of match. So I'm going ahead and I want to make sure 50 samples per second should be enough. We're not going to be working at very high frequencies in terms of cyclical frequency, but you may want to double check that. But let's go ahead and let's start our experiment. So we are going to press play and we're going to displace the cart and then we're going to measure the frequency. So I'm going to do this all at once. It doesn't really matter because we're going to have enough measurements. but you can start ahead of time if you want to. Beautiful. So see, you can actually start it and run it again too. It doesn't really matter. So like I can just go ahead and start, and I can collect as well. It's a pretty consistent, it's not perfectly the same each time. You see it's kind of slowing down. It's slowing down due to friction, so we don't have a perfect system, but it's pretty nice, I have to say. So we don't see some dampening effect. So that's our first experiment. Let's export that data. And then what we're going to do is we are going to compare this with another setup that we're going to show just in a bit. So now that I've tried and failed to do that, one of the interesting things is you can see that our initial position has changed. So for our equilibrium position, but that's a little bit beyond the scope. You'll learn that more about that in vibrations. So I'm just going to displace it again, and I'm going to collect the data, and we're going to export that data. So let's go ahead. Oops. Make sure it doesn't click off like you just saw there. So actually, I'm going to start it in the other direction. So I'm going to start in this direction, and I'm going to go let it go. Much faster. See? But here, I'm going to actually collect the data now. So let me actually try to do this at once. There we go. And from our equation, we should sort of expect that. So let's export this data, and let's do one more experiment now. Now for the last experiment, what we've done is we put a 250 gram mass on our cart, or whatever mass you want to do. So we're going to displace it again. Oops, let's keep it straight. And we're going to let it go. And then we're going to capture the data. There's a little bit of sliding of the mass, but it's not a huge deal. And you can see, obviously, the big difference in how slow that's moving. So let's go ahead and let's analyze our data, and we'll see you then. So let's start to analyze some of our data, and let's go ahead and do this in Excel together. So we're going to want to calculate the frequencies, and we're going to also want to plot this as well. So let's go ahead and get started. So I'm going to go to File. I'm going to open, and I'm going to find where my file is located, which is in a thumb drive. And I want to do all files because it's going to be a text file. And it is going to be this file right here. So this is for the system where we have 2 red springs, and there was no additional mass on my cart. And we have position, acceleration, etc. So this is great. So let's go ahead. And we will go ahead and insert. Let's go ahead and create our. I like what Series 4 was doing. So let's see if we can. But I'm going to do scatter. So let's go ahead and just do a scatter. Ooh, let's see what Series 1 says. Let's look at this data set. Let's select the data. So that's A and B. That looks good to me for Series 3. A and B. It's only going to 132. Is that it, though? That is true. So I'm just going to go ahead. Again, I expect you all to make it look very nice, but I'm going to go ahead and remove this. I'm going to remove this. Here, we're going to make it a little bit better. So let's go ahead, and we're going to have the axes labels. We had it for 5 seconds. This is great. But we're going to format this. Yeah, let's add a line to it. Again, we need axes labels. So this is acceleration this is position in meters on my y-axis. On my x-axis, we need to add that and call it in time. But I'm going to grab the points. So I'm going to actually select some points here. So for example, I can select this location. Actually, what I'm going to do is I'm going to actually also increase this. So let's go ahead and see. We can actually see if you hover it over. So it was at a time, our x-axis is 0.66, so 0.66 seconds. And we can move over here 0.66, and 1.42. So I'm going to go into Mathematica now, and my period, T, and I'm going to label this. So this is T, red, no mass. Although no mass, no additional mass in the cart. But that was going to be 1.42 minus 0.66. So then my F, red, no mass, is going to be equal to T, red, no mass. Actually 1 over. And then our omega is just going to be red, no mass, is just going to be equal to 2 pi 2 times pi times F red, no mass. Excellent. So that is our frequency, or our circular frequency experimentally. Now, theoretically, the red spring had a spring constant of 10 Newton meters. So our function would be square root of basically 10 plus 10 divided by the weight of the cart is 250 grams. Now, we do have some additional hooks in there, so you may want to weigh the cart if possible, but that's pretty close. And especially considering the cart's more likely, probably about 0.3 grams. So we're right on it there. So beautiful. So now we're just going to repeat that for our other measurements. So our next measurement we did red, blue, F red, blue, red, blue, and then finally X red. So we mix this, and then, so the blue should have a spring constant of 20. So if we do that, now let's go ahead and open the file there. File, open, mixed with no mass. Let's go ahead. We're going to insert our plot. Oh, how come it didn't? Yeah, if I click on it, it's a little bit nicer. So I'm going to go ahead. I'm going to go in here and find the data, select the data, edit the data. A and B, I do want that. So maybe I don't want this. Don't want that. Let me just make sure again. A and B looks fine to me. Good. So I can zoom this up. Zoom this out. So 0.42. 0.42, and then let's say 0.42, and let's say 104. So minus 1.04, and then this, what was this point? 0.42. 0.42. And we can look at this. So we see it's definitely, and we saw in the video too, is faster, so that makes sense. Slightly faster here. Red, blue, no mass, and voila, beautiful. And finally, we can do our last data. So actually, I'm going to click here because this was mixed as well, but now we added an additional mass. So let's go ahead. Not no mass. Red, blue, because there was a mass. Red, blue. Point. So now we were doing 0.3. Let's just be accurate. 0.3 plus. It was a 250 gram mass there. So you can look at that. Slower makes sense. Let's go ahead and look at the data. Let's open it up. Let's browse again. Mix with mass. Good. Tab eliminated. Insert. Let's go ahead and click on this. Why don't we have? Click on this first. No, please let me get away with. So I'm going to go ahead and click here. I'm going to do the same thing with selecting the data. Probably again, like so. There we go. Let's zoom it up. So now let's go to 0.86, 1.74, 1.74, 0.86, 1.74 to 0.86. Here we go. Red, blue. Here. And again, right on the money. Beautiful. So make sure you include these calculations. Make sure you include graphs, and we'll see you in the next lab for some materials, hopefully. So see you then. Thanks. Bye.